Test, test, test. I think I'm working now. Good. Yeah. All right. Let's see. Welcome back. Bayesian Cognitive Modeling. Day 9. I'm your host, Keontae. Today we're going to be continuing off where we were from yesterday. And we were at the tail end of the latent mixture models chapter. And we were doing individual differences in malingering, I believe. So let me just pull up the problem. If you're curious about what we're doing here, if this is your first time tuning in to the live stream, is I'm just going through each of the practice exercises in this textbook by Lee and Wagenmaker from 2013 and discussing what this code means, talking about what this model is specifying, and just overall trying to build up some intuition surrounding how do you go about interpreting Bayesian outputs, so inference from the posterior surrounding all of these parameters. How do we go about setting these parameters in a way that informs our particular questions and makes sense in the context of the research design, and doing all this properly takes time, skill, effort, perseverance, what have you, etc. But we are just going to keep practicing this. I don't know where to put my mic. Still working on mic handling and stuff. I think this is a good height. I just really want to be able to sit up straight and have the mic hear me. And I think that this gets the levels right. Yeah. Perfect. Yeah. Okay. There. And now you can see my face a little bit. Okay. So anyway, we are in individual differences in malingering, I believe, and we're going to be answering these questions. I might have spoken about what this model is doing at the end of last episode yesterday, but I don't even remember if I did because I'm like 7 presentations deep now. I actually had a presentation earlier today I gave on data simulation. So I'm just talking through code all day. And, I love it. So it's fine. This is fun. Right, so we're just going to start with going over what the problem is again. What were they interested in understanding about the world and why they go the rationale for constructing this model in the first place. And then we'll talk about some of the particulars. I'm just pulling up some notes and okay. So let's go through it again. So in this case, remember, we're interested in identifying if people who are taking a test that is supposed to classify them as having a memory deficit such that they could receive financial compensation. We want to know if they're cheating, if they're malingering. Cheating on these sorts of tests there's incentives for them to cheat on this test, so we want to know if we can identify subjects who are deliberately performing badly, and from those who are just performing, right? That way, this is sort of a cheating detection system, which we can be used in the future to inform insurance practices, maybe for identifying people who are trying to pull the wool over their eyes on having some sort of memory deficit. Right? So we set up an experiment where we asked subjects to a set of questions, and we said, okay, some of them are bona fide, where they are deliberately trying their best, and some people are asked to not to intentionally try poorly, to underperform. So we want to see if we can latently identify these groups using a mixture approach, so inferring these groups based on the scores on their test. And we went ahead and did that in the first case. However, what we didn't do in the first case is, or what we did do in the first case is we assumed that every subject had the same success rate. However, we know that subjects can have different success rates, so we want to account for there being variation on the subject level as well. And that's unique information, right? So here, that's what we're gonna do. Let me just familiarize myself again. Right. It seems restrictive to assume that all members of the group have the same chance of answering correctly. Right, so some people might answer better or less that are part of the group, and not have this average success rate that we are implying across all of the folks. So instead, so now individual binomial parameters, so the success rates for individuals are all from a group level distribution, which is specified by a beta distribution. And we call this a beta binomial. And this is a transformation of parameters, right? So we're using alpha and beta here, where the group mean is equal to some combination of them, and lambda is equal to some combination of them. So this is the number of questions. This is the score they get. We're going to infer the success rate, and we're going to have two success rates. One for the bona fide and one for the malingering group. And this indicator, or the baseline of this indicator, can vary. We have a beta 5.5 is uninformative, right? It's like a fairly uninformative prior, like, I think. And we're going to estimate the mean for the malignant group, the mean for the, we're only estimating the mean for the bona fide group, lambda for the bona fide group, which are uniformly distributed by these parameters. And then from that, we can determine what the mean of this group is, because we have the difference. So we know the difference between this and this group, which can give us this. So we estimate the difference and this term, which allow us to calculate this. And then we also set a prior for the lambda for the malignant group. Gaussian with an interval. So this difference ensures that we constrain it so that there's only ever going to be a difference in the direction of the bona fide group performing better, which makes sense because subjects didn't listen to the instructions if they performed as good as the bona fide group, because the test isn't challenging, especially for someone who doesn't have a memory deficit. So let me pull up the code then. So this is WinBug's code. I'm going to pull up the JAG's code. And we're malingering too. Right? Set the working directory. Okay. Here's the success rates. Here's the latent group indicator. We have some uncertainty surrounding those thetas. Okay. And then over here, 20 subjects. 22 subjects, each of which we're going to get a Z for, which Z is our indicator, right? We're going to get a theta, so theta 1, 1. Why do we get 2 thetas here? So this is the rate that we would estimate for a person. They're all high. So this is the rate we would estimate for a person if they were in the first group, and this is the rate we would estimate for a person if they were in the second group, and then from those values we make some determination about what group they're from, right? So let's see, example wise, 93, 65. Let me make sure I'm I'm not cap right now. This looks like I'm not seeing what this is saying correctly. Let's see. So each person belongs to one of two latent groups. So this specifies the indicator for the latent groups, where we have a Bernoulli distribution for the base rate, and we're going to estimate the baseline needed for the probability of them belonging to one or the other group, and we add one to the indicator so that we can do stuff with it. So relatively uninformative prior for the base rate phi, right? Data are binomial with a rate given by each person's group assignment. So for each person, we have a k at I. So for a person, we have a binomial, and they're going to be from theta z for whatever one they're from, and then n is the number of questions. I see. So while we estimate all these, we don't use all these, right? So for example, for Z15, they're from this group, the 0 group, whichever that one is. Malingering group, I assume. So if we looked at 15, we estimated a success rate here for 15, but this is the success rate that gets used here. So about chance, performance wise. Transform group mean and precision. Oh yeah, I mean, don't forget these, right? We also have the averages. So the average success rate, bona fide group, average difference between the two is, and then give me the average malignant is about chance. Cool. This phi is the value that gets used for the baseline for the binomial distribution for when we're trying to identify if you belong to one group or the other. So based on that, it's likely you belong to the malignant group because we have more folks in that group. And then these are the variability. So the variability for the... Oh, these are lambda, right? So that's not even interpretable. I don't want lambda. I want sigma. I could calculate sigma. But I guess because I'm not really interested in those parameters, we don't. These are like nuisance parameters here. But if I wanted to have some estimate of the variability, that was... Well, I can just calculate it using this. What is it, like 1 sigma is equal to 1 over the square root of this? So not. And here. So a little more variability for the malignant group. Malignant. Malingering. So transformed parameters then, just to make sure we're clear. Alpha. Right, so notice we don't pull these parameters. We just use them to calculate these parameters that we want. So we needed alpha and beta, which can be derived from or described from these. And then we use the logit scale here. And we get alpha and beta for the second group as well. And there we go. And then we have these parameters constrained to be, the difference constrained to be positive, bona fide group. Where am I defining mu here? This is what I want. Logit scale too. Are these scaled differently? No, because I use logit here. So this is like a hierarchical structure, right? With built embedded in the model, where we estimate certain parameters so that we can estimate other parameters of interest to us. In this case, we're using the beta binomial sort of thing, where I estimate alpha and beta in order to get information about mu and lambda. Right. Here then, number of people, number of questions, the data that are getting passed on the drags, initialization. So we initialize z 3 times. And why do we initialize z 3 times? What does this look like? Oh, we're just getting a difference. Difference. Oh, so we're initializing z. We're initializing z and mu diff 3 times here, because we have 3 chains, right? That's why it looks different from what we've seen in the past. Normally, what we've been doing is only using a single chain. Now we're using 3 chains here, probably following some of the specifications that were set in the paper, maybe. Staring at the screen a lot today. And now we have parameter z, theta. So these are all the parameters we're interested in. So notice that we don't call for alpha or beta. We just use alpha and beta in the model. Okay. Is the inferred rate for malingering consistent with what is known about the instructions given to the participants? So we can observe that by looking at the first 10 subjects and seeing if they are all bona fide, which would make them equal to 1. So from z. I'm sorry. Not bona fide, I mean. Let's see. I think the first group is bona fide. 0. Bona fide 1. Malingering. Based on these results, probably the first 10 people are bona fide, all correspond to the experimental manipulation. However, if we look at these subjects, we have 2 subjects who don't correspond. And part of that is how they score. They scored 44s, and 44s is really close. In fact, it's some of the people who are bona fide. So we know that they just didn't listen to instructions, because that's something that someone who knew it would have been able to do it. Assume you know the base rate of malingering is 10%. Change the code to reflect this knowledge. Mm-hmm. Changing the base rate to 10% is this, right? So the only thing I want to do then is I don't want phi. I'm just going to use 10%. I think this should work. So now we don't get phi. No phi, you see. This is just based on this now. To be honest, the code was actually just doing it wasn't using the base rate. I knew I was reading this right. So this has to be the phi, and then like this. Right, yeah. Shoot, I need to include phi. So I was just looking at the results without phi. Let's look at the results with phi. Oh shoot. What did I do wrong? Oh. A nice crash to start us off. It's fine. Let's run it again. Why did it crash? I don't know. But we will try again. Let me close some things. Maybe I'm just running a lot of stuff too. Better. And we're still getting the same results. Notice we do get a slight variation here. No. I'm just streaming it. So we still get only slight variation here for the grouping, the latent grouping, but overall results are like I was talking about before. Now that before we were just pulling phi, but phi wasn't getting used for anything. Now phi is being used. However, it's only slightly perturbing this value. And what we saw before, it was like flat these before. So it's not really changing our results for the classification between bona fide and malingering. Assume you know for certain that participants 1, 2, and 3 change the code to reflect this knowledge. So it wants me to incorporate information. I don't know. Would it just be down here? I'd like add information. I mean, it's doing the guessing pretty nicely. Yeah. Okay, I see. So each person belongs to 1 or 2 latent groups. So in addition to this for loop, you just write out the belonging to each group. So you do something like person 1. more specification here, I think. Let me see. So we're not defining NZ, we're just defining them to a group. In this case, 0. Bona fide is 0. Let's see. And then this might break now. Alright, it didn't break. The probability of success rate did not change. Though we still estimated the first 3, it looks like. We would get no stochasticity surrounding them if we... How can we check? Oh, we just do this. Now I say, oh, say they're part of the other group. If this works, then my declaration made it so that I'm controlling which group a given person is from. Let's see. First 3 people. See, so this is how I know my fix is not working, because I'm not getting anything there. Okay, so let's see. Basically, what it wants me to do is instead just describe a vector range for these initial values that is restricted such that it doesn't include these 3 values in it. Yeah. That way, we're not randomly generating values across the first 3 indicators, because we're using the knowledge that, okay, I know that these 3 subjects are part of the control group, so I don't need to tell my simulation to consider them when we're going to try to extract latent grouping for the remaining subjects. So yeah, there's a couple solutions, it looks like, but the solution that they suggest is just creating a vector that is a restricted range where we don't include the 3 indicators from the first for the first 3 subjects, right? Okay. Let's see. Next question. Assume you know for certain that participant 1, 2, and 3, they did that. Suppose you add a new subject. What number of questions answered correctly by this participant would lead to the greatest uncertainty about their group membership? Maybe 40? We can check that. Say we add a subject. Oh, how do I stop? I can't stop it. That's not gonna work then. It's just gonna break. Oh no. It's literally gonna break. Okay. It didn't break. 40. Is pretty low, but not high. Not high as the others. So look, we got this 50%. Yeah. A lot of uncertainty then about where it should lie in the group. So around 40. So even 39 might be. Let's see what happens with 39. You know, doing this for 9 days straight in addition to all my other stuff has been really, I'm glad it lines up nicely with other things I'm doing, because I could feel how I could definitely get tired of grinding through these exercises. In fact, you know, today's Friday and this is one of the last things I want to do today. Other than some assignments, I have one assignment I'm going to try to finish today, but it's definitely weighing on me right now, I will say. Okay, so let's take a look. Oh, so no, even 39 seems to really push it over. So one last thing, we'll try 41. But 40 seems to be that nice spot. Nope, and that puts us back over to the other side. So it looks like 40 is that special value. Yeah, it puts us at like 50% here. Okay. Try to solve the label switching problem by using a uniform distribution with mu equal to bona fide instead of the Logit transformation. Okay. First, maybe a little more context about this label switch. Right. Notice the restriction, uniform distribution psi, which prevents the indeterminacy or label switching problem. Okay. So in our case, items recalled. Cheaters. I think this is my first question I'm stuck at. I got this though. So instead of doing this Logit transformation thing, it wants me to use do the sort of restriction range specification that we have been doing prior examples, where we create a joint distribution where one is specified by the other, I think. I'm just not sure what to change here. I could use some guidance. What is Trinity? Oh. Jags 1, Jags 2, Jags 2 model N, model R2. Nunca. Okay. I'm not really sure on this one. So the label switching problem, like we saw in prior questions, has to do with potentially one grouping and the other grouping switching. Or if we're not careful about doing some range restriction in our priors, then it's possible that there can be some indeterminacy in which group is supposed to represent what. And so what we're supposed to do here, or what it would like us to do, I'm guessing, I'm going to move forward admittedly, so, but what the question wants us to do is create this joint distribution where we specify mu bona fide from 0 to 50, and then we specify mu for malignant as equal to 0 to bona fide. Right. Okay, no. So mu malignant is equal to u bona fide, and u bona fide is equal to the total distribution, u1. So this looks like this up here. Let's see. This. So this is the mismatch match. Instead of doing the logit thing, we just do something like this. But it's also in the context of our model. So in this case, alpha would be equal to a uniform distribution. Beta would be equal to a uniform distribution to alpha. Ooh, I think it's tough. Perhaps the internet can help me solve this problem. Alas, that's the extent of where we're going to get with that, so we can try to get this last problem in the half hour we have, so that we can start off fresh tomorrow. So what are the priors for, why are they different? So this is something we noticed over here. We have different priors for each of the two groups, and this is essentially saying we're specifying that there's going to be more precise estimates for one group than the other. And here, the more precise estimate, if I'm understanding correctly, I wish there was like I'm looking for the tool. I'm sure there's like a shiny app. So the first one's like pretty uniformly flat. So it's like 40 across 800. The other one is 4 to 100. far more diffuse. And part of that is because these values are all going to be very informative, but we want to leave space for the precision. So we use this type of uniform distribution, very diffuse from my understanding. D uniform. I'm just looking for something to plot the uniform distribution so I can build an intuition here. So sort of looks like this. Starting at 40, increase. That makes sense. So at 40, the probability of these values becomes higher. So the probability low of being from the bona fide group when you're below 40 on the score. Okay. That makes sense. And then let's see what happens if we do 4 to 100. And then we just extend it out. So this, once again, 4. 4 is like super sus. But then everything else standardized across values. Now, it's clear we don't have values in the 800 or 100, but we just set it. So we have this difference in variability, I guess. Okay. All right. Interesting. So we were just, we can use expert knowledge to sort of identify what would be some solid priors for these. Where it would be natural for us to think that the variability in the bona fide group should be less because it should all be high, since there's only a set possible answers that would indicate that they tried, because the test isn't hard. Now we're going to apply this, looks like, to Alzheimer's research. All right, in this section, we apply the same latent mixture model in 6.7. 6.7. To different memory test data. Nice. So we're using this model we have that's supposed to identify bona fide and malingering. And we're going to apply it to people with Alzheimer's. The practice raises the possibility of people cheating, writing down the words they're being asked to remember. So this data come from an informal experiment in which 118 people were asked to either complete the test normally or instructed to cheat. The particular test used a complicated sequence of intermediate and delayed free recall tasks, which we simplify to give a simple score out of 40 for each person. By design, 61 bona fide people who are known to have done the task as intended, and 57 who are known to have cheated. It changes the names of the variables from malingering to cheating as appropriate, uses different priors using different priors for the precision, and makes the mean accuracy rate for the cheaters higher than the bona fide group. Right, so this is changing the direction where cheaters this time around are going to be those who perform really, really well. And so we know they're cheating because these are fairly complicated tasks. Okay. For each person, baseline, Z, you set the parameter there. For each 4, 1 to P, group assignment, K, theta temp. Oh, let's go make sure. So in this case, we have theta temp binomial or beta distribution of alpha beta. Then theta is going to be, theta for the first group is going to be the max of this min. So the success rate is going to be the maximum where I see, so it's this success rate for one group is going to be described from this, where theta temp is going to give us the value for this. Likewise, theta temp. Is this how the problem above did it? I have to talk through this one then. Because after we do that, PC keeps track of the accuracy of each classification made in sampling by comparing each person's assignment to the truth of the experimental design. So it's a model accuracy. On the classification accuracy. Okay, let's pull it. This is interesting. All right. Luckily, we've been going for. Okay. So let's see if the code's the same here. So these max descriptions are, yes, we assign a temporary theta, and then we are max, where here, and then the minimum of this. So the range we're looking at for max is from this to whatever the minimum of this is, where the range is this to this, where we estimate these values. And that's going to give us our success rates for each of the two groups. And then we're doing the same sort of transformation for the group mean and precision. And we set uniform and equivalent priors for the precisions for both of the groups. And now here we count. So truth. Where's truth? Oh, so we have a vector of the true scores here, and we're just asking a logical is what we thought equal to what we did get, and then we're just summing, so we get a proportion of accuracy. Looks like this is going to make us some plots too. Nice. But here, if we're looking, so we open up the cheat, CSV, and I'll take a look at that after this runs. And then apply the sum, so we're going to get the correct per participant, and satisfied by k. We get the late of k up. Let me fix this so it doesn't do that. Let's try again. It's like I was saying. Then we're going to look at, we have to import pkn truth, initialize the two chains. Here, the two chains are going to be equal to p so enough z's for all the p's. Difference, we want phi, we need, whoa, okay. Just spit a graph out on me over here. Number recalled. We'll take a look at that in a second. When we specify lambdas, starting values, mu starting values. This bona fide cheater graph is just a little wonky. Maybe I can just shut these off. Maybe I do this. It doesn't even give me a plot then. Alright, so I definitely need at least these parameters. Oh, maybe the plot is, oh, plot's over here. So maybe I can do this. Nice. But what happens when that's there? Restricts it. Gross. Hmm. So we output these 3 plots. Nice. Okay. So top summarizes the data showing the distribution correctly recode from each group. What do we see? Cheaters seem to be recalling a lot more. So this test is out of 40. Cheaters are on average recalling a lot more than the people who are asked not to cheat. And in fact, let's see, number of items recalled correctly increases, right? And the total distribution of success seems to be somewhere in between 0.75, 0.78, with the discrete amount being around 35. The accuracy achieved using various cutoffs on separate groups. What's the description or accuracy achieved by the latent mixture model? The line in the bottom shows the classification accuracy for all possible cutoffs, which peaks at here. So a cutoff of 35. I see. So when we set the classification accuracy to 35, that being when we consider someone who .35 is the cutoff for whether you're a cheater or not, we're getting something that's very close to what we'd expect, given the true values we know. So if you get more than 35 right, it's more likely that you're a cheater. So you see that here, and you see that here. Using a generative model to solve the classification problem is unlikely to work, as well as the best discriminative methods from machine learning. This is not because of failings of Bayesian approaches, but because the models we develop are imperfect accounts of how the data are generated. So we could do better, essentially, is what it's saying. But we wouldn't use this sort of generative model, which is, we would just use a machine learning approach where we wouldn't be estimating all these parameters to build a model. We would just aim for prediction and use something like a neural net, or something that's really, really good at classifying people on the basis of the data, underlying data. But this provides us information about the process that we can assume are producing the data. Particularly here, we're getting to quantify the uncertainty associated with let's see, the relationship between the number of items recalled correctly, and the posterior classification belonging to a cheating group. So, like we said, 30 probability you're a cheater, given that your value is over 30 is high. We see the trend here where the probability of being classified as a cheater increases at some rate as a function of the number of questions answered correctly. So we're not sure about these folk, but we can be sure that these folk are bona fide with high confidence. These folk are in like the middle waters. These folk are cheaters. And we can use this information to save us money, as it described here. If screening tools cost this much and this much, so we only need 80% certainty. We're talking about certainty here. Let me print out the Z's so you can see what we're talking about. We don't even ask for the Z's. Yeah, we do. Where are my Z's? Is it just too long? Oh, reached maximum. Is there a way to print samples? What does print samples look like? That's not going to work. So I can't just print out the Z's, it looks like. If I want to access the Z's, I gotta go do like samples. And this isn't even going to give me the probabilities. Damn it. How do I set the max print? I don't know how to set the max print. Oh, well, we're definitely going to get that at least today. Yeah. That's right. So here. So people like this, or sometimes it's very high, but we have people edging 80, how many 60s? I'm over 60 or something. A 70, see a 70 would be in that middle zone we weren't looking for. Not enough certainty. So we get this expression of uncertainty that one person's a part of one group or another, which could be useful. So we could set some sort of threshold and use that threshold when considering follow-ups and catching cheaters on these sorts of diagnostic exams for Alzheimer's and stuff. In this case, Alzheimer's. We get the cheaters average is pretty high. Bona fide people, though, do this well. Here's the percent accuracy. So the model's performing pretty good, but not perfect. So it's not a perfect expression of the data. The uncertainty surrounding the estimates for the two groups differ slightly, though not enough to say that they don't overlap. So the difference is slight, though, and that's what makes this problem hard in the sense of sometimes people are bad cheaters, I guess is the way to think about that, where sometimes people don't know actually how to cheat or don't cheat correctly, and so they don't get inflated high scores. Okay. Suppose the utilities are very different so that the false alarm costs $100. $100. So 25. Because the risks of litigation and false accusation but misses are harmless, costing $10. Right, so this is nothing to do with changing the model. It's changing these threshold values. I'm curious how they landed on these values. This 80%. Classify people. 4 times more likely. So 25 in the hundreds. Now we have 100 to 10. So it's less costly to
throw out cheaters. Is that what this is saying? So it's less costly to, it's not costly to miss someone who's cheating, but it's more costly so raising a false alarm for someone who's cheating is more costly. So we don't want to misclassify people who are cheating as cheaters. So this threshold might go down. So more liberal. Or it would increase, right? Because we want to we want to guarantee that cheating's cheating. So these values would just move slightly to the right. So let's see. Cheaters then would be something like here. Or we're thinking about 0.1. So it would be up here. So cheaters would be here, because we don't want to flag or whistleblow on people because it's costly. It's 10 times more costly. So we're willing to incur some cheaters because it's less costly than identifying a cheater falsely. So we set the threshold now 10 to 1 here. So this group would be cheaters now under this new framework. Is that the only question? Oh, there it is. Last question. What other potential information besides uncertainty about the classification does this model provide? This model provides the average. I spoke about this. It provides the average for the two groups, the difference between the two groups, baseline. The model also gives us, it said other than the uncertainty. So this is the uncertainty in the latent grouping, has to do with Z. Predictive accuracy is PC. Which is, not bad, I would say, but not terribly good, I guess, at the standard of a discrimination sort of machine learning algorithm. It would be interesting to apply that, though, to the data set. Different time. Yeah, so I'd say the averages is one piece of information. The ratio, which we know should be a specific amount, but that kind of, yeah, that's not as informative. Nice. Basically everything I said. I'm just viewing what some general answers to this question could be centralized around. So averages, like we said, so we get an average for cheating. Tends to be around this, the difference. Some variability in performance across the two groups, which reduce very slightly, though are similar in terms of variability. Baseline also. Sex rate cheating, but this is the baseline for our classification problem, which is about 50%. So notice how these are characteristics that we have available to us because we used Bayesian inference in order to make estimation about the decision-making process in this case. Though if we fit a machine learning model, it'd be more black box, where we wouldn't have access to things like the averages and stuff, and the difference. We would just have some classification. So this performs well, and we get some interpretation out of it. So it goes back to those traditional trade-offs between interpretation and accuracy or predictive accuracy. Great. Nice. Model 2, part 2. Alright, so we've made it. We have made it to the second section, or the part 3, the third section of the book. So we've made it all the way through parameter estimation, going through latent mixtures. We went over some traditional data analysis problems that we might occur, as well as just inferring rates. So now we're going to talk about, now that we've gone through, all right, how can we estimate parameters that are informative to with respect to our research question. We're going to say, well, what if we can have multiple models for how this given system might work, right? So I might say one decision process cheating model performs better than the other based on some difference in the parameters or some difference in trying to think how to say this. Good thing I'm going to read. I'm going to learn about it. But this is going to essentially be a way how we did go and make some principled decision surrounding choosing between the performance or the quality of a given model with respect to some other model. So this is going to open us up to some sorts of conventional hypothesis testing techniques that are commonly used within Bayesian inference, and that we will use when we're trying to make assessments about the quality of one model versus another in terms of its fitness for answering questions about our research hypothesis. I think, or research questions. So thanks so much. Have a great weekend, and I'll look forward to seeing you tomorrow, and we'll get started with model selection. Yep. And